I've talked about how using a diffraction grating we can get fringes that are very narrow, so that it's a lot easier to measure distances between fringes. Alright, as well as fringes that are a lot further apart because the slit spacing is very small. And this gives us more accurate measurement of x, which would allow us to calculate wavelengths more accurately. What I'm going to do next is to derive an accurate formula without this approximation sign. So first, let me redraw this in a schematic way. I'm just going to look at the side view. I'll start with my grating. So let's say I look at this grating from one side. So it looks like this with lots of slits that light can go through. Now the distance between two slits, I'm going to call it D instead of the A which I used earlier. So as we have seen in the last example, A is typically about 1 micrometer. Very, very small distance between slits. Okay. Right, and so some distance away would be a screen. So that's the screen where we can observe the fringes, and that would be the grating. I'll continue to use my example of a green light coming through here. So this green light is a light wave. Think about this. It has having these wave fronts that would travel, and the wave front gets split up into many tiny sets of waves that would diffract, spread out, and interfere at the screen. So this would have a certain wavelength lambda. Okay, and on the screen we would expect to see fringes. There will be one at the center. There will be one some distance away. Another one further away, and so on. Okay, so let me think about a light ray going from one of the slits to one of these fringes. So let's say this one. One from there and one from the neighboring slits. Okay, if I think of the screen as quite far away, these two rays of light would be almost parallel. So once again, I'm going to use the method which I used previously. I'm going to consider a little triangle here. I'm going to work out the difference between these two paths. Okay, and I can get that if I draw a perpendicular from this slit to this next ray. Okay, perpendicular line. here. Okay, that's tricky. Let me do something else first. Let me draw a horizontal line from them in between those two slits to the screen. Okay, that's horizontal line, and another horizontal another line to the from in between the slits to that fringe. And what I want to do is I want to relate this angle here, this angle theta, which I can actually measure, all right, by measuring the positions of position of that fringe. I can actually measure this angle. I want to relate this angle to the difference in the two paths from one slit and from the next slit. Now, in order to do that, I need to magnify this part. I need to draw this part up again. So let me draw it down here. Okay, so that's my A. That's spacing there, and I have that two paths going out, very nearly parallel. Okay, parallel paths, and I have this horizontal line, and I have, which is 90 degrees to the vertical grating, and I have this line in between the slits, also parallel to the two rays, and I have my angle theta down here. Now, I'm interested in relating this angle to the path difference. So the path difference is given by that means that the difference between this path and this other path I can find by drawing a perpendicular from one slit to this next ray, the perpendicular line, and this distance here would be the path difference. Right, this distance would give me the difference between this length and this length. And as we understand from the double slit experiment, that for constructive interference, in order to get a fringe, that distance must be a whole number times the wavelength. Okay, so that peak would meet peak down here and trough meets trough. Okay, so I have this connection, and as we have also seen from the Young's double slit videos, this angle here, this angle there, is the same as this angle, theta. Okay, now we are almost done. That's a right angle, so that means that this is a right angle triangle. Now, since this angle is theta, now this A here is the longest side of this right angle triangle, and this n lambda here is opposite the theta. So the relation is sine theta. The relation between this and this is sine theta. Let me write that down. So therefore, sine theta is equal to opposite over hypotenuse, n lambda divided by A. Good. Now Actually, I would prefer to use D in this case, because that's sort of more standard for this diffraction topic. So instead of A, I'm going to call the distance between the slits D. And I'm just going to change this name, D, to the distance between two slits. That should be D down here. Okay, and that's the formula that I was looking for. So if I just rearrange this into another form that is also commonly used, just by multiplying both sides by D, I move D over to the left. I get D sine theta is equal to n lambda. Okay, so now I have a formula in which I can find lambda. For example, I can find the wavelength if I know D, the spacing between slits, which you would normally know very accurately from if you buy the grating from a manufacturer. It would be given specified for the grating, and so you will know D accurately, and theta we can measure also accurately by setting up these experiments. Okay, by measuring the distance between the center fringe and that fringe, and then the distance between screen and grating, for example, or just setting up an instrument to measure the angle directly. So we can measure theta, and from this we can calculate lambda. And as to the value of n, it is related to the fringe that we're looking at. So for the central fringe, n would be 0, because the central fringe is at the same distance from the two slits, or from other slits as well, because this, remember that the grating is very short compared to this distance. Okay, so but I can just look at any two slits, and the central fringe would be same distance from them, so n is 0, path difference is 0 for the central fringe. For the next fringe, as we move up to the next fringe, right, the path difference will increase. As we move up, and the first time we get constructive interference, and therefore that we see a fringe, is when the path difference increases from 0 to 1 wavelength. So therefore n should be 1 for the first fringe, and if we move up further, the path difference will continue to increase, and when we reach 2 wavelengths path difference, we would see the next fringe. So that would be n is equal to 2. Now the other direction is symmetrical, so for this slit, then n is also 1, for that one n is 2. So that's how we can determine n, depending on which fringe we want to look at.